Hi everyone. In this video, we will discuss the last of the three major theorems from multivariable calculus, the divergence theorem. Before we begin, however, it's important that we understand what the divergence of a vector field means and how we can integrate it over volumes in R3. So we want to begin by defining the divergence of a vector field, specifically on a vector field in R3. So let F be a continuously differentiable vector field, which we will express in terms of its components. So the vector field F is equal to P times I plus Q times J plus R times K. Then the divergence of F, which we often denote just as div of F, is the scalar field. Divergence of F is equal to the partial derivative of P with respect to X plus the partial derivative of Q with respect to Y plus the partial derivative of R with respect to Z. Now, if we recall this sort of formal vector del, this vector of differential operators we had discussed before, we can also write the divergence of F as the dot product of del with F. So if we consider this here, right, I simply have I have del dotted with my vector field F, which has components P, Q, and R, right? And now I take the dot product, again, recognizing this isn't really a product because what I mean by ddx times P is just applying this differential operator to P so that I get dp dx plus dq dy plus dr dz. Okay. So again, this is just a way of sort of an alternate way of denoting this. Okay. So we can very easily, once we have this, right, we can very easily compute the divergence of a vector field. In fact, it's much easier than computing curls. You don't have to take some cross product, right? So just as a quick example, right, if I gave you the vector field f of x, y, z and told you it was x squared y, comma, sine of y, comma, let's say z squared cosine of x. And so here's a vector field defined on R3. So we could very easily compute the divergence of f here, right? Now, remember here that the divergence of f, it's a scalar field, right? So I'm going to add these things together. I'm going to get some scalar function back, right? So I'm first going to take the partial derivative of the first component with respect to the first variable, right? So dp dx, that's the first component and the first variable. And so that would just be 2xy plus, okay, dq dy, that's really the partial derivative of the second component with respect to the second variable. So that would just be a cosine of y. And then finally, we would have a partial derivative of the third component with respect to the third variable. And so that would be 2z cosine of x. Okay. And so this gives us the divergence of f. It's fairly straightforward to calculate. You just take some partial derivatives, you add them all together. Now, I want to emphasize here that what this divergence, if I think of this as sort of an operator, right? It takes as an input a vector field, right? So I take a vector field, I feed it into this divergence operator, and what happens is it spits back out to me a scalar function, right? And so when I say this is a scalar function, right, this is a scalar function on R3, or I mean, you could, if you wanted to more specifically define this on some subset of R3, right, then it's on whatever subset that P, Q, and R are all defined, right? So that's fine. The actual computation of it is not like anything super complicated, right? But what we want to move forward with understanding is, well, what does it really represent? Now, before we jump into that, you'll notice that we have defined the divergence here as if it's only something that we can talk about on R3. Now, when we talked about curl, The way we defined curl as a sort of cross product, right, of del with a vector, it's unclear how that would work in any dimension other than 3, right? Now, it's worth noting that there are ways of generalizing this notion, and if you go in, occasionally we offer what's often referred to as Calc 4, which is sort of a manifold theory type course. You would discuss this in greater depth. But it's not immediately obvious how to generalize curl beyond R3. Divergence, however, right? Yes, I have it written in this form, but you notice that language I used of derivative of the first component with respect to the first variable, derivative of the second component with respect to the second variable, derivative of the third component with respect to the third variable. If we have a vector field on Rn, you sort of feel like you could just keep going, right? You would add a plus derivative of the fourth component with respect to the fourth variable, plus derivative of the fifth component with respect to the fifth variable, so on and so on. And indeed, right, we can do that, right? So this very naturally extends to higher dimensions. We're really going to be focused today on R3, but if I have a vector field that's just defined on some subset U of Rn that maps into Rn, and it's continuously differentiable, and I just call the components F1, F2, all the way up to Fn, then I can just define the divergence of this vector field on Rn as the sum, k equals 1 up to n, of partial derivative of the kth component function with respect to the kth variable, right? So, again, this divergence very naturally extends to all of Rn. Okay. Now, the natural question that comes out of this, once you realize you can compute it, is that's great, but what is it actually measuring about a vector field? So you'll recall we said curl measured sort of the rotation of the vector field, right? So the curl of a vector field was another vector field, but that curl vector at a particular point gave you sort of an axis of rotation and sort of an angular velocity, about sort of how fast it's spinning at a particular point. I'll note that if you think about what happens when you try to extend that into higher dimensions, like that notion becomes less clear. Okay, so that's again one of the reasons that the curl is a little harder to extend, although it can be extended to higher dimensions. Divergence, on the other hand, you can think of as measuring this sort of instantaneous rate of expansion of a volume of some small region which you allow to be carried along by the flow of F. So the way I often think of this is, imagine that this is some sort of like a water stream, right? So these vectors are telling you how the water is flowing. And imagine you drop in a little drop of like food coloring, okay? You wonder, sort of, is the flow going to take that little drop, wherever I drop it, is the flow going to take it and expand it out? Or is it going to contract it? But instantaneously. So right at the second it hits the water, is it going to get like blown up, or is it going to get compressed? And at what rate? That's really what divergence is measuring. So you can imagine maybe sort of like, here's your little drop of dye, and if all the flow vectors are going out from the place you drop it, right? When you drop it in there, that little dot is going to instantly expand. Okay, we would say that's positive divergence. Okay. Now, it's also possible that you're in a situation, and I've drawn these as sort of curvy arrows, but you could even imagine, right, like you have something like this going on, right, where things are looking sort of like this, right? So you're actually getting this sort of rotation, right? And so you drop the dye in, the droplet in of food coloring, and it doesn't change at all, right? Maybe it's just sort of spinning around in place. That would be zero divergence, okay? If you drop it in and all your flows are coming in, right, then what's going to happen is, well, however big that dot was, it's going to get even smaller, right? It's going to be compressed, right? So we would say that's negative divergence because that volume is going to be contracted at instantaneously when you drop it in there. Now, these are sort of idealized representations, right? It can become very difficult, right? If you are sort of looking around some particular point here, let's say, and you have maybe a big vector like this, and another vector like this, and another vector like this, and maybe another smaller vector like this. Like, you ask the question, okay, I drop sort of some some dot in here, what's going to happen? Well, after a little bit of time, like this part is going to be pushed out a lot because that's a really big vector, but this is maybe going to be pushed out a little bit, but it's a smaller vector. And this is going to come in. So maybe after some time, what happens is you have, something like this. Okay. Well, I mean, I guess as I've drawn it, it looks like that's bigger, but maybe it's not, right? Like, and this is sort of, an approximation. So it's not always the case that something is just nicely expanding or contracting, right? You can have these weird things where maybe on one edge it's sort of contracting, on the other it's expanding. And what we're really trying to understand is how this total volume, right, is instantaneously being transformed, right, as you drop it into the vector field. All right. So again, divergence in some sense is just measuring, for each particular point. Well, another way to sort of think about this, if you're familiar with the sort of source sink terminology, is sort of, are we at a source where things are expanding? Are we at a sink where things are being contracted, right at that particular point? And of course, in a vector field, you have some, a bunch of points that are sources, a bunch of other ones that are sinks, some that are neither, right? Things are just rotating around. Like all sorts of things can happen. This can be different at every particular point, but the divergence is measuring that at each particular point. All right. So we want to sort of think towards this thing that's going to be called the divergence theorem. And so what I want to think about, the sort of fundamental question here is, what if I wanted to integrate the divergence of some vector field in R3 over some volume V? So here's the idea. I'm in R3. And I have some volume enclosed over here. So again, I'm not thinking about a surface now. I'm thinking about some solid three-dimensional region, right? So if I think of this as sometimes we're like a lumpy potato here, right? I'm not just talking about the skin of the potato. That would be a surface integral, right? I'm talking about the whole potato, right? I'm talking about the whole interior of this region. Okay, that's my volume V. So I could come in here, right? And so at each point inside here, I could calculate the divergence. So I could calculate the divergence there, calculate the divergence there, calculate there, right? At every point in V, I calculate the divergence. And then I want to add it all together, right? Fundamentally, that's what integration is, right? So I want to sort of add all these together. And the question is, well, I wonder what I ought to get, right? Now, when we think about doing math, right, it's hard to prove a theorem if you don't have some thought about what you might want to get. So right now, we're sort of in the exploratory phase of like, what do I even think ought to happen? Okay. Well, anytime you're thinking about integration or sort of approximating these things, it's always a good idea to break things up. So back to my potato analogy here, I'm going to just sort of imagine I'm going to go in, I'm going to dice the potato up, right? So I'm going to get a whole bunch of little cubes. Now, ignore the fact that, right, on the surface it's sort of lumpy, and so near the edge, okay, it might not be exactly a cube, but just imagine I go in and I just sort of dice this whole potato up. Okay. Now, what I'm going to do is I'm going to zoom in here, and I'm going to pick out a little section of this dice. I'm going to sort of zoom in on one particular section. In particular, I'm going to pick a section that still has part of the skin on it, right? So I'm not pulling out a piece of the interior. I'm pulling out some parts that are interior and some that are on the surface. So I'm going to denote things that are on the surface. They'll be sort of shaded in pink here. So I'm going to come in here and I'm going to zoom in here. Okay. And when I zoom in, I'm just going to end up with this thing that looks sort of like a bunch of cubes glued together. And, I'm not a great artist, but it's okay. Yeah, maybe we just have like a couple of here. All right. So sort of diced up, right? And again, I want to imagine that this face, right, this face here, right, is the one that's actually on the outside of the, it's actually on the boundary of this volume. All right. So first, let me imagine I go in here somewhere down inside, okay, and I pick something out of the middle that's not on the surface. So I pick out something, I pick out one of these little guys that's totally in the interior. Okay, so this is my interior piece. Okay. Now, let's think about if I think about now I've got a vector field that's defined on this whole thing. I can think about right along each cube, along each face of this cube, right? There is sort of a single vector. Now, of course, I'm thinking infinitesimally, otherwise there'd be many, many vectors. But there's sort of one vector of the vector field on each of these faces. So maybe this one is a big one pointing out, and this one is a little one pointing in, and this one is a little one pointing out. And so each face sort of has one of these vectors. Okay. So think about what's happening. I want to think about, okay, what's the divergence then sort of at the point that's represented by this cube? So, well, here my volume is going to be expanding. Here it's going to be contracting. Here it's going to be expanding. It's hard to say totally what's going to happen. Okay. However much the volume is expanding in this direction, the cube that's immediately attached to this face, this front face, it's going to be contracting by that same amount, right? There's another cube attached right here, right? Sort of another little ghost cube sticking off of here. And so the fact that, yes, my orange cube I'm looking at, this face is expanding, this other one is actually contracting because they share that same face and they have the same vector there. Similarly, however much this one is expanding, there's another little ghost cube sitting over here that is contracting by a corresponding amount. However much the top face is going down, there's another little cube sitting up above this, right, that's expanding by that amount. So on the interior, my divergence on this cube, who knows whether it's positive or negative, but the amounts, whether it's positive or negative, there's a corresponding magnitude, but opposite change of these other things. So if you add it all together, for things on the interior, you ought to get zero, right? However much this volume is expanding or contracting, it's being offset by expansion or contraction of the other elements of the interior. Okay. Now, what happens though if I take one of these guys on the edge here? Okay. So again, I have a little vector sitting on this face, and maybe it's pointing. Oh wait, sorry. This is my surface, right? This is the piece that's actually on the exterior of the volume, on the boundary of the volume. Maybe that one's pointing out. And let me actually emphasize here, right? These vectors, this one doesn't have to be oriented nicely and normally to the surface, right? It could be that the vector that's here is sort of out, but in a sort of not the normal direction. Okay. And then on the rest of these sides, right, I have some, maybe this one goes in, who knows? Okay. Now, let's think about what's happening here. Now, whatever amount we're expanding up here, right, that's going to be absorbed by the next little piece sitting up here, right? So yes, maybe this is expanding in volume, but it's compressing the one above it, okay? Yes, maybe this one is contracting, but it's being offset by the cube on the other side of it. Same is happening with all the other faces except for this piece of the surface. Now on the surface, what's happening, right? Well, on the surface, If this is expanding, that's fine. But it's not being offset by a compression anywhere else because now we're outside of the volume we're integrating over. We're not adding in another piece of this. So what we see is that all of the contributions of the divergence get canceled out except for whatever happens along the surface S that bounds this volume V. Okay. So then we ask, well, how much is this expanding? Well, at this point, right, maybe this isn't a nice vector, right? But I could look at how much of this is actually normal to the surface. So if this is my vector F, sorry, if this is my vector F in red, right, this vector here is the normal component of that. Okay. So what I'm saying is, if I integrate the divergence over this whole volume, pretty much everything will cancel out on the interior. I'll just be left with, and this is the punchline of the divergence theorem, I'll just be left with the values on the surface that I need to add up. So I'm going to take a surface integral of the vector field, and that ought to be all that remains. Okay, this equation is the crux of the divergence theorem. Now, of course, we need some conditions. Okay, we've just drawn one picture and sort of said, oh yeah, that seems right. So we've got to do a little more work, but this is exactly the idea behind the divergence theorem. All right, so let's first formally state the divergence theorem, and then we will look at a proof. So the divergence theorem says let V be a solid in 3 space bounded by an orientable closed surface S. So again, as we're thinking about this, I have some sort of, blob in 3 dimensions, right? And the V is this sort of whole volume, right? Again, so I want you to imagine this is 3-dimensional, right? And V is the whole filled in solid. Okay. S is the surface of, so it's just the outside of this volume, right? So think of this as sort of, there's the box, the cardboard box, that's S, and then the volume V is all the stuff inside the cardboard box. Okay. Now, this condition that S be orientable and closed. So closed means exactly what you think it means, right? I just don't want this to be, I don't want this to be some sort of infinite volume. That's not a nice closed thing. Orientable is a little more, quite a bit more actually technical. Okay. This is not something you typically get into in a lot of depth in a Calc 3 course because what it means to be orientable, I mean, eventually, in a pure mathematical setting, you want to go on and talk about manifolds and what that means for those things to be orientable. And that, again, is you need to define things in some different ways to do this in general. For our purposes, I think the way of thinking about an orientable surface is the surface has some normal vector that varies continuously, right? So as you move around on the surface, right, you don't, so for example, move around and come back to this point and end up pointing in the other direction. So you don't have things like, Klein bottles or Mobius strips. Those are non-orientable things. This is basically, I have a nice normal vector, right? There are 2 sides to this surface, sort of the inside and the outside, right? All of these things are related to orientability. Okay, so we have a nice solid V. It's bounded by an orientable closed surface S. And then because we're going to need to do a surface integral, we need to define a normal vector, and we want n here to be the outer normal vector. So it's a normal vector that's pointing out from the volume V, right? Okay. Again, if it wasn't orientable, you would have trouble defining this, right? Because there wouldn't be two nice sides and you couldn't easily define an inward and an outward normal, okay? All right, so if we have that set up, and if F is a continuously differentiable vector field defined on V, that basically makes sure the divergence will be defined, okay? Then the triple integral over this entire volume of the divergence of F ought to be equal to the surface integral of F ds, okay? So this again is that sort of equation that we last justified. We sort of conceptually made sense of why this should be true. All right, so this seems reasonable, okay? We'll certainly want to prove it. Before we do that, though, I want to take a slightly closer look at this. The first thing we can notice about this is, okay, F is a vector field, and there are a couple of different notions now, at least two, right, we've seen of taking a derivative of a vector field. Somehow the curl of F was somehow a derivative of the vector field, and now we have this divergence thing, which is sort of like a derivative of a vector field. So what we're saying here is that I can swap out this triple integral of a derivative of F for, okay, this isn't a double integral, it's a surface integral, but it's an integral over a two-dimensional set, which is the boundary of this three-dimensional set of F. This sort of looks like a fundamental theorem of calculus, right? I can essentially replace one of the integrals, right, and take the derivative off of F. Right? So it sort of looks like a little bit like a fundamental theorem of calculus. Okay. Now, if we think about what would the divergence theorem, well, this is in three dimensions, but what would the divergence theorem say in one dimension? Okay. So what if we were just in R? Well, what is a volume in R? It's just an interval. Okay. So an integral over a volume in R would just be the integral from A to B of, okay, well, what's a one-dimensional vector field look like? Well, that's a vector field with one component. That's just a function, right? And the divergence of a vector field, that's just a derivative with respect to that one variable. This is just the derivative of F with respect to the one variable, okay? So in one dimension, this left-hand side becomes the integral from A to B of F prime of X dx. Okay. And now what is this saying? Okay, now this is an integral over whatever it is that bounds this interval. Well, A and B, the 2 points A and B bound this integral. What does it mean to integrate over a 2-point set? It really just means you add the things together. Okay, so what do I need to do? I need to take F and evaluate it at that point. So let's start with F evaluated at B times the unit normal vector at B. Well, in one dimension, the unit normal vector is the number 1. Okay. And notice that again on the interval AB, right? That is the outward normal derivative, which is what you want n to be. At A, you need the outward normal derivative. That's just going to be -1. Okay. So you get plus F of A times -1. So this just becomes F of B minus F of A. And what I want you to see is that if the divergence theorem in R, it's just the fundamental theorem of calculus. Okay. Now, what if we go to R2? Okay. If we go to R2, okay, well, what's a volume in R2 look like, right? Well, that's really the double integral. And here, if we write down what the divergence is, it won't really immediately be clear what it is we ought to do. So here, this would be dp dq dx, dp dx, plus dq dy. Yeah, this is the integral over some double integral over some region. So if I wanted to apply Green's theorem here, I look at this, this isn't quite right. For Green's theorem, I would want dq dx. So what? I would really want like this to be q, and then I want a minus dp dy, so I really want this to be like minus p. Okay. So if I sort of think about that and apply Green's theorem, what I would get, what I would get then by applying Green's theorem here, so I can think of this instead as I really have, I guess the other way to think about it is like a minus, and then you have a minus q here, okay? And so what you end up with is the integral of, so basically notice that p and q were swapped, or so instead of getting like the line integral here of p dx q dy, you're going to get minus q dx plus p dy. And now you look at this and you sort of go, well, this isn't like I don't know how to make sense of this, right? This seems a little strange, right? I feel like what I ought to get is the integral over the boundary of the vector field dotted with the normal vector. Well, think about, we always have that the normal vector for a curve, right? For some curve here, the normal vector to the volume is always orthogonal to the trajectory. Okay, so we really can think about this. How do you get an orthogonal vector? You swap the components of the vector and you negate one of them, right? And so this really does become, and I'm being a little hand wavy with some of the details here, but if you want to incorporate the normal vector in here, this really becomes the integral over the boundary, over that boundary, which is just a curve of the vector field F, which has components P and Q dotted with N, right? Something like this. Okay. Now again, that's a little hand wavy at the end, but it gives you the idea that again, this is really Green's theorem, right? That this in 2 dimensions, you're really using Green's theorem. It's really somehow encapsulating what happens with Green's theorem. So what I want you to see is the divergence theorem. We already really know it in R and R2. Now we get to know it sort of in Rn, or sorry, in this case in R3. All right. So that's great, but how are we going to prove this, right? So what do I do if I want to formally prove this? Well, it actually turns out the proof of this, and again, it's not shocking because of what we just discussed maybe, the proof is actually quite similar to the proof of Green's theorem. So, well, I guess there are elements of both Green's theorem and Stokes' theorem in here, but again, that's not surprising. We use Green's theorem to prove Stokes' theorem, and we've already seen that Green's theorem is just the 2-dimensional version in some ways of the divergence theorem. All right. So we're going to first do a little bit of setup, okay? And so we're going to refer to our vector field F in terms of its components P, Q, and R, okay? And we also want to express our normal vector in a slightly different way, okay? Now to help you sort of make some sense of this, I'm going to express my normal vector as cosine of alpha I plus cosine of beta j plus cosine of gamma k. And your first question should be, okay, fine, but what on earth are alpha and beta and gamma? So imagine you have your surface, right? And again, this is, I need to be careful. This is some closed surface, right? So maybe the surface, again, this is the exterior of that volume, okay? And you have on that surface some normal vector. Now I'm going to to help illustrate my point, I'm going to really exaggerate, you know, the length of that normal vector there. Okay. Now, what you can imagine is at this same point, I take a unit, or any vector really, that points parallel to the x-axis, right? So I take, in this case, so if this is sitting in R3, right, I'm going to take a vector that is parallel to the x-axis, and I can then measure the angle between these two vectors. Now, right, you should imagine, so this one is sort of pointing up, and this one is pointing out, right? And so you end up with some angle between them. That is alpha. So the x component, what this is really doing is measuring how much of this normal vector is in the x direction, where alpha is just this angle here. For the second piece, I would take a vector in the parallel to the y-axis, okay, and then measure this angle here. That's beta. And now cosine of beta j gives me sort of the component of n that's pointing in the y direction. And I think you can probably see how this is going, but then we take a vector purely in the z direction, right? We can measure this angle here, that's gamma, okay? So all we're really doing is expressing this normal vector in terms of its x and y and z components, okay? All right, so if we do that, we can write out, this is just the triple integral of the divergence. And this is going to be equal to, I can now write out for this surface integral what f dot n is, right? So this is p times, this is the x component of the vector field times the x component of the normal vector, plus the y component of the vector field times the y component of the normal vector, plus the z component of the vector field times the z component of the normal vector, right? And so this is this surface integral. All right, so just as we did before, okay, the way we're going to prove now this, right, which is equivalent to the divergence theorem, just expressed in a slightly different way. The way I'm going to prove this is I'm just going to equate things. So I want to show that the triple integral of this term is equal to the surface integral of this term. I want to show that the triple integral of this term is equal to the surface integral of this term. And I want to show that the triple integral of this term is equal to the surface integral of this term. Okay, so that's exactly how I'm going to prove it. I'm going to prove this one big equation by proving three smaller equations, right? So, and I've broken them out here, right? So it just suffices to establish these three equations, and then if I add them all up, adding all these up would give me the triple integral of the divergence. Adding these up would give me the surface integral of f dot n, right? All right, so to prove this, we're actually going to, the proofs of all three of them are more or less the same. We're going to prove this third one, okay? So we're going to prove that the triple integral over the volume V of dr dz is equal to the surface integral of r cosine gamma. All right. So let's start by looking at the, we're going to start by looking at that triple integral, right? Okay. So, or sorry, before we do that, let me talk a little bit more about this surface V. So I'm going to assume, just as we did before when we did prove Green's theorem, right? We assume that we're working with sort of a region of type 1 and type 2. Well, in 3 dimensions for volumes, it's a little more complicated. We want to assume, so we want to consider a volume V bounded between g of xy and f of xy over some set t in the xy plane. sorry, the XY plane. So the idea here is I have some upper surface, sort of this upper surface, which I'm going to call f of xy. I have this lower surface, g of xy. And these are both sort of surfaces that are defined over some set t that's sort of laying down here in the plane. Right? So I have this set t laying down here in the plane, and I have these two surfaces above it, and I'm really looking at the volume sort of directly trapped between these two surfaces, right? So again, I'm looking at this whole volume, right? My surface S that bounds this volume is this upper surface and this lower surface, and then sort of the side surface, right? And in fact, I want to even denote those differently. So I can think of this as, say, sort of S1, this lower surface is S2, and then the side as S3. That'll be helpful later on. All right. So if we do this, now if I look at the triple integral over V of dr dz, okay, and instead of writing dx, dy, dz, we sometimes just write dv for just sort of a generic volume element. Because, right, we could do dx, dy, dz, we could do dy, dz, dx, right? The order of integration we can swap around, so we'll just call it dv. Okay, but in fact here we want to compute this in a particular way. Namely, we want to compute this first with respect to z. So if I think about this region, okay, this is all the z values which are bounded between g of x and f of x. So I can write this as an integral where z goes from g of xy to f of xy. And then my x and y values, they just need to be in this region t. So I can re-express this triple integral as a double integral over t of the single integral of dr dz dz from g of xy to f of xy. And now this is just the area element to go with this. This is either dy dx or dx dy, however we want it. But now if I look at this single integral, I can apply the fundamental theorem of calculus, right? So still have the double integral on the outside. But now this just becomes antiderivative of dr dz with respect to z is just r. So this is just r evaluated at z equals f of xy minus r evaluated at z equals g of xy. So this is just r of xy f of xy minus r of xy g of xy. And then dA. All right, so this triple integral is equal to this particular double integral. Now, I want to sort of flip to the other side of the divergence theorem, and I want to show, let's now look at or sorry, not the full divergence theorem, but of the sort of piece of the divergence theorem that I'm trying to prove, right? I'm now going to flip over and look at this surface integral of r cosine gamma ds. Okay. Now, it's a surface integral. Remember, we're taking it over this whole surface, so top, bottom, sides. Okay, but I can break it up, right, into a surface integral over the top plus a surface integral over the bottom plus a surface integral over the sides. Now, let's think about, remember, okay, what was this gamma? This gamma was the angle between the normal vector and the unit normal pointing in the z direction. So if I think about what's happening on S3 here, on the sides here, all of my normal vectors are going to be pointing parallel to the xy plane. So if at these points I also take the vector, the unit vector in the z direction, so this is just the vector k, okay, that angle is always going to be 90 degrees, right? So on these sides, all the normal vectors are parallel to the xy plane. This k is pointing straight in the z direction, right? This might be moving around, but it's always in the xy plane, so it's always orthogonal to this. That means that this gamma is always going to be 90 degrees, or pi over 2. Cosine of 90 degrees, or pi over 2, is 0. So this term disappears, since on this surface, gamma will always be pi over 2. Okay, so it doesn't matter what r is, this cosine of gamma term is always going to give you 0, and this whole surface integral will be 0. All right. So that's fine. We can get rid of that. Okay. Now we need to deal with these two pieces, this S1 and this S2. Now we're going to need to erase a little bit to make a little more space. So let's do that. But again, remember, our goal is going to be to show that this is equal to this double integral. Right? That's going to be our goal, because if we can show that the surface integral of r cosine gamma is equal to this double integral, we already know this double integral is equal to the triple integral of dr dz dv. All right. Let's give ourselves a little more room. I'm going to keep erased a little bit of that picture, but we want that picture might be helpful still. Now, the next thing we're going to take advantage of is the fact that for S1 and S2, because these are surfaces that are defined by functions f of xy and g of xy, we actually get a very natural parameterization. Okay. So let me fill in my picture here. So I want to parameterize, oops. Parameterize S1. Okay, so this upper surface, we're just going to parameterize it as x, y, f of xy, right? And S2 down here as xy, g of xy. Really easy to parameterize these surfaces that are just graphs of functions. Okay. So if we do that, then on S1, okay, so if we look at S1 and we take the normal vector, okay, so on S1, so we're going to do this piece by piece. We'll see a lot of this really ends up being the same. But on S1, the normal vector will have the same direction, right? Whatever it is, it'll have the same direction as the fundamental vector product, okay? So on S1, n is in the same direction as dr du. Again, here with our parameterization, we're using x and y. So I'm going to say dr dx cross dr dy. Okay. And so if I look at the surface integral over S1 of r cosine gamma, that ought to be equal to, well, this is just the surface integral over S1 of R. So why is this true? Well, our surface integral here, right, this is the z component, right, of the vector field. So it's only going to be really like the z component of the surface integral here. And right, the z component, if you think about how we were able to break out this in terms of the dx dz, dy dz, and dz dx, right? This is only the z term that survives, right? Because this is just the z component of the vector field, okay? So we get this, and of course, we can express this, right? By definition, this is the double integral of, you take R, you evaluate it on the surface. Okay, so there's my capital R evaluated on the surface. And then in this case, this should be like whatever this wedge, whatever this product is, right? We would have in here a term which is partial xy, partial like uv, but again here for our parameterization we're using x and y. If you calculate this, this will be 1, right? So here you just get this, okay? Similarly, if you make a similar argument over S2, you get that the integral over S2 of R cosine gamma ds, okay? Now here we need to be careful because we're going to pick up a negative sign because here the normal was pointing up. Now the normal is going to be pointing down. So we're going to pick up a minus the surface integral over S2 of R dx wedge dy. But this is just going to be minus the double integral over T of R evaluated on the surface x2, which is g of xy. And now I know that the double integral over all of S of R cosine gamma, right, that was equal to, we broke it up over S1 plus S2 plus S3, but over S3 it was 0, so we just got the double integral, or sorry, the surface integral over S1 of R cosine gamma ds. So this is what we did shortly before I erased last time. And now we've shown that this is this double integral and this is this double integral, which if we combine them together, gives us the double integral of the difference, R of xy, f of xy. Give me a little more space here so I don't have to erase a lot more. Minus the double integral, minus this double integral, but now we're combining them, of R x y g of xy d x dy, which is precisely what we had shown earlier is equal to the triple integral of dr dz. Okay. And so we've proven one of those three equations. Now, to do the others, you assume that V has a different form, okay? But fundamentally, the idea is you prove that if V has these sort of different forms, just like before when we assumed for Green's theorem that we were looking at a region that was both type 1 and type 2, right? Here you're going to have like a volume V, which satisfies 3 different conditions. But if you can prove it for this volume V satisfying 3 different conditions, you can actually prove it for all sufficiently nice volumes V by partitioning V up into regions of this nice type. Okay. So that concludes the proof of the divergence theorem, and in fact concludes our entire discussion of multivariable calculus. So in the next video, we will begin, we'll return to Bill Baldry's book, and we will begin our discussion of Lebesgue integration. And in order to do that, we're going to be doing quite a bit of set theory early on, because in order to be able to integrate things The first thing we need to be able to do is agree upon a way of measuring the size, or something like the length, of a set. And we will begin that in the next video.